Now we consider an application of the roll-down summation formula. We study the theta function. Theta function is this function theta, defined for positive variable. Theta x is the sum exponential of minus n squared pi x. So this is the theta function. This is a kind of special function. In our study of ordinary differential equation, we encountered the Bessel function, the random function, and so on. Okay, all these are the so-called special functions, which are very useful in mathematical physics. So theta function is important. We will prove this property of theta function. Then theta x equal square root of x, theta 1 over x. This is the relation of the value of theta function at x and 1 over x. Okay. To prove this result, we need to take a function and apply the Poisson summation formula for that function. A suitable function is alpha. Given alpha positive, we consider fx equal exponential of minus alpha x squared. Then we notice a useful integral. The very useful integral, but we have not proved this yet. Let phi y equal 0 positive infinity exponential of minus x squared cosine 2xy dx. Okay, this is an integral which is parameter y. Integral for x, for a function of x which is parameter y. Therefore, the integral is a function of y. And this y, this integral, the value of this integral depends on y. But it turns out that this equal 2 square root of pi exponential of minus y squared. Okay, this is a useful result. Unfortunately, because we have not discussed the integral which parameter, I have an exercise for the integral. I have several questions about integral which parameter, but those integrals are for bounded function over bounded interval. In this interval phi, we are encounter unbounded interval. So the result provided by the exercise is not sufficient to study this integral. But I can give some idea for computing this integral. We might assume that which the theory of integral which parameter this we can take in derivative under the integral sign. That is phi prime. That is phi prime y, that is dy the integral exponential minus x squared cosine 2xy dx. This can be written by 0 positive infinity, taking partial derivative exponential of x squared cosine 2xy dx. And this is equal minus 0 positive infinity exponential minus x squared, then 2x sine xy dx. Then because of the 2x here, you can move this 2x inside the integral, inside the differential, to obtain dx squared. Then you can move the exponential inside integral. So this can be written by integral 0 positive infinity sine xy and sine xy d exponential of minus x square, then integrating by part. This gives us exponential minus x square sine xy for 0 positive infinity divided by 0 positive infinity exponential minus x square d sine xy. Okay, can this be true? Integrating by side, by part. Yes, but the first term is 0. When x goes to infinity, exponential minus x squared goes to 0. When x is 0, then sine xy is sine 0, therefore it's 0. So this is 0. So the result is equal minus 0 positive infinity exponential of minus x squared. Then d sine xy, what is d sine xy? D sine xy is y cosine xy. Y cosine xy dx. Then we obtain the minus y 0 positive infinity exponential minus x squared cosine xy dy. That is minus y phi y. So phi prime y equal minus y phi y. That is phi y satisfies an ordinary differential equation. Phi prime y plus y phi y is 0. And also we have initial value problem, initial value condition. Phi 0 y. Phi 0 y, I should write here. Phi 0 when y is 0. When y is 0, phi 0 is the integral 0 positive infinity exponential minus x squared. Cosine 0 is 1. Okay, so phi 0 is the integral of from 0 to infinity for exponential of minus x squared, which is half of square root of pi. Okay, so solving this initial value problem for ordinary differential equation, you can compute the phi y just as given here. Okay, so anyway, this is phi y we know how to compute. Of course, in this computation, this step is problematic because how can you move the differentiation inside the integral sign? But this is justified by some theorems in the theory of integral which are parameter. Okay, so we are done. We know the result of this integral. Now, with this result, we can prove the property stated here for the theta function. We make some computation. Minus infinity, positive infinity, exponential minus alpha t squared, exponential minus 2 pi int dt. This can be written by twice of 0 positive infinity, exponential minus alpha t squared, cosine 2 pi nt 2 n pi t dt. This is easy. You divide this integral by minus infinity to 0 and 0 to positive infinity, and make a change of variable for the first integral, that is for negative part. Then you will obtain another exponential, which this one you will obtain the twice of the cosine. Okay, this is easy. I will not repeat that here. Then this integral is almost of the form of our phi y. Our phi y, remember our phi y we just compute. Our phi y is the integral 0 positive infinity exponential minus x squared cosine 2xy dx. So we need to write this phi. We need to write the integral we want to evaluate by the form of phi y. Therefore, we make a change of variable, that is 2 square root alpha 0 positive infinity exponential of minus x square. That is, we let this alpha t square to be x square, or x be square root of alpha t. Make this change of variable. Then this integral become 2 over square root of alpha. Then cosine t is square root of alpha 2n pi x divided by the square root of alpha. Then dt is dx. Dt is dx divided by the square root of alpha. Okay, so we are now at this stage. But what's this? This is the y. This is for y equal, consider this as y. Then this is 2xy. Just the form of phi. Okay, so this is equal to 2 square root of alpha phi n pi square root of alpha. That is by our result of the value of phi. Phi y is pi 2 exponential minus y square. Using this result, our phi evaluating at this point is 2 square root of alpha, then 2 square root of pi, then exponential minus the y square. Y square is n square pi square over alpha. So that is pi alpha a half, then exponential of minus n square pi square alpha. Okay, we have this computation. Now, by Poisson summation formula, our theta alpha over pi is just the sum m from negative infinity exponential of minus alpha m square. This is the definition of theta function. Definition of theta function here. Okay, let x to be alpha over pi. So m square alpha. Okay, that is m square alpha. Then by Poisson summation formula, this can be considered as the Poisson summation for f x equal exponential of minus alpha x square. Then this value is just fm. This value is just fm for our this f. Okay, so so we apply Poisson summation formula for this function fx equal minus exponential of minus alpha x square. Okay, so this gives us by Poisson summation, this equal n equal minus infinity positive infinity exponential of minus alpha t square, that is ft, then exponential of minus 2mi pi 2 pi I n t dt. This step we use Poisson summation. Okay, here we use Poisson summation, and the right hand side, the integral on the right hand side we just computed, right? in this page, we just obtained the result for this integral. We just obtained the result is, so the result is here. Okay, so copy the result. We get this is the sum n minus infinity. Pi alpha square root exponential of minus n square pi square alpha. And the square root of pi over alpha can be moved out of the summation. Thus, pi alpha a half summing exponential of minus n square pi square alpha. But this is just theta at the value pi over alpha. This summation, by the definition of our theta function, this summation is just theta pi over alpha. Let's call that theta t. Theta x. Our theta x, I write it here. Theta x is the sum of exponential minus pi n square x, So this is the comparing this sum, which is the definition of a theta function. You know that this is the value of theta at pi over alpha. So theta alpha over pi equal theta pi over alpha multiplying the square root of pi over alpha. So we go to the next page. That is theta alpha over pi equal pi over alpha a half theta pi over alpha. Now we let alpha equal pi x. We obtain the theta x equal square root of x, theta x. Okay, so this is what we want to prove. Useful property of theta function. Okay.